AI model. Now, before you start building an AI model, you have to think, what kind of data do you have? What do I want the AI model to be aware of? So in this case, we might have a box of X. And in this X, in this image, you can think, oh, maybe I want to localize the X. So we'll draw bounding boxes around the X. And then I will show those bounding boxes to the model. The model uses that for training, and then it can infer the location of those X. Maybe instead of detecting, you also want to do classification, because there was not just chicken X, there was also duck X there. Or you're not doing bounding boxes, but you want to know the size of the X. So in this case, you draw a polygon or a mask around the X. And that's often a lot harder to annotate, because, well, you need to draw with a pencil or some kind of a tool around the X, and that's error-prone, because you might have to do this like 100 or 200 times, and after 200x, you're gonna make mistakes because you want to go fast. And for that reason, we built a lot of tooling around this to make it easier to do this kind of segmentation tasks, also for bounding boxes. But in this talk, I'll really focus on this segmentation task. So quickly about me and our team, there's some other people from my team here as well. We're building Geti, which is an open ecosystem for training AI vision models. We are part of the Intel's Edge AI Client Computing Group, part of the Interactive AI Group. We are based in Groningen. We have we had a small office nearby. That's been cancelled. Some difficult stories, but hopefully we'll get something back. And our main goal is to make it very easy to build and use AI on Intel hardware, because, well, we are at Intel. But typically, all our tools also work on other NVIDIA, etc. Marketing might not want me to tell that, but yeah, it does work. Big plus is that our code is all free, and it's also open source on GitHub, or at least sort of open source. Check the license. And here's a quick video of the product we're building, and I'm mainly showing this to give an indication of like why we had to do this. And I recorded myself annotating like I think 500x in maybe 3 minutes. So that went very, very fast, and it's kind of fun to do that as well if you're like in the zone. So now, what will we talk about? I gave a quick introduction about why we invested this time in this. I will quickly show the manual tools, and that gives you an indication of how boring it is to do it with the old tools. Then I will show you how we applied classical computer vision algorithms using OpenCV. OpenCV is a library that's very well known in the computer vision communities for doing any vision kind of tasks. It's mainly C++ based, and we had to compile to the browser, to WebAssembly for the browser. I'll show you how we did that and some gotchas in there. Then we saw that the smart tools with classical computer vision weren't really good enough, so we invested some time in using neural networks locally in the browser. And finally, I'll have some concluding remarks, etc. So here's 3 videos, and they're starting too quickly, but that show the manual tools we have. So we had the bounding box tool that's quite quick. You draw a bounding box around your egg, and that's it. We can also do the same with a circle or an ellipse, but that's not really accurate. And then the other way would be to use a polygon tool. So either you draw every point individually by pressing, or you could draw it by just holding down your mouse, or if you have a tablet, you can do with a pen as well. But these are quite error-prone. Like it takes a lot of time to use high-quality data, and you want high-quality data, otherwise your model might not be that great. So we were looking for better tools. And the first thing we tried was building smart tools, so to say, so tools that are interactive using OpenCV. First, the requirements that we had. First, we want to have a very low latency, that when the user interacts with the tool, it has to give a result within like 200 milliseconds. If it takes longer, the user gets bored, they might dismiss it, especially if there's bad results, because the tools can be smart, but maybe they don't always give good results. It has to be accurate, otherwise it's not useful, and then refinable. So if the tool gives you an output that's not really what you want, you need to correct it. The first thing we started out with was GrabCut, which is interactive foreground extraction using WebWorkers, which is quite a reasonably well-known algorithm that pioneered interactive segmentation tasks. If you've ever used Photoshop, they use some of these tools internally as well, even before the AI hype. A good thing is that it has first-party OpenCV support. So basically, you can just run GrabCut in OpenCV. You do need to do some extra things for improving the results. And then it has this iterative refinement. First, it's not very visible, but I drew a bounding box around the middle egg. Then the tool gives you this result where it draws a mask around the egg. But here you see at the top that it has some parts that belong to the other egg, and I don't want that. So what we do is we correct it by drawing negative markers, and then we run GrabCut again, and then we get a good result. So that's the promise. But how do we run this in the browser? Because OpenCV is it's written in C++, and well, you can't directly run C++ in the browser, but you can compile it to WebAssembly. The OpenCV library releases their version every time with their own OpenCV.js file, which you can use, but it's quite big. It's 9.8 megabytes, which if you consider like the images and the models that we also use in our same platform, it's not that much because sometimes our users use like high resolution images of 3000 by 3000 pixels. So it's not that much of a problem, but it does make loading OpenCV slower. So that's why we looked into compiling our own version of OpenCV. And I think it's not going to fit in the slides, but we manually compiled it using these commands. I'll show some other code during the talk. You don't have to understand it. It's mainly to give you an impression on how things are. I will publish these slides online on GitHub later after the talk or after the weekend. We give this configuration file, and this configuration file essentially contains all the code that we need from OpenCV, and it's really slideware code because it's all tightly put together, but this contains all the functions that we need. And with that, we could reduce the build to be 2.1 megabytes, which is a lot smaller, and it loads a lot faster. So it was quite a big win for us, and it was very easy to do. You just need to spend some time in reading the documentation. Documentation is not always great. It does a decent job. So if you can't understand it from the documentation, just ask your favorite LLM, and then they will do a pretty good job in understanding things. Now, some notes. Our team uses TypeScript and React as a base language and framework. And the OpenCV from so far, there's no official support for TypeScript. And that's quite a pity, because it makes it a lot harder to work with. In the community, there have been several people and companies that try to create this package to build TypeScript types out of the C++ interfaces. And what we did is we were pragmatic, and we just copied those interfaces and put it in our own code. And that did a really good job. It does have some false positives and such, but it was okay for us. It allows us to build all the things we need. Another thing that people that tend to write front-end applications aren't aware of is memory management. When you're using this OpenCV and with some areas where you use WebAssembly, you need to do manual memory management where you have to delete your memory after using it. So the code looks roughly like this. You first create this matrix objects for a source and a destination, and then you do something with that, and finally you delete the data. It would be amazing if we could somehow build and compile OpenCV.js with the using keyword. That's a kind of new keyword that is available in the latest JavaScript and TypeScript, where if you are aware of C++ smart pointers or with in Python, you can essentially delete this when the variable goes out of scope. That would be a lot easier and a lot less error prone, because I think we still have some memory leaks here and there. But typically the browser does a decent job at fixing those. So we don't have really big issues with that, but it's still something to consider. Now, I will show you some slides that show how OpenCV and GrabCut works. First, I had some code that displays it, but I think that will be very difficult to understand. So instead, I'll have some steps. So first, we draw this bounding box around the subject that we want to annotate. And I did this a little bit rough so that it would make mistakes, so that that's obvious. And here you see the resulting mask that GrabCut outputs. It's actually not this color, but I made it this color just to emphasize some things. There's the outer background, which GrabCut will ignore completely because that's outside of your bounding box. Then the blue area shows the extracted background that GrabCut thinks is background. And then the orange one is the foreground, which will be your resulting mask. And you can refine on top of that mask. What we do is we do a threshold. So we say ignore all the background things. Then we generate a contour from the threshold, also using the same OpenCV kind of tools. And then we generate a polygon out of that. So basically just taking the points of that contour, and then you have your nice polygon. And all our tools in Geti, they all use shapes where we have a polygon of points, and we don't use masks. So that's why we need that. And at the end, we optimize the polygon, because sometimes you get a lot of points, and you don't always need that accuracy. Like if there's 2 points, and you have a line, and the points intersect, you can sometimes remove them. That's essentially what this does. Now, this works pretty well, and it's fast. However, if you have a slower device, and you have higher resolution, then you could block the UI thread. And when that happens, your animations get blocked. And that's why we use WebWorkers. And WebWorkers essentially allows you to go from single-threaded to multi-threaded in a sense. So long-running computations, whenever we run algorithms, we move that to a WebWorker. And yeah, without that, it feels a lot less interactive. One other thing is that we use a library called Comlink from Google Chrome Labs. It's not that well known, but if you're in front end and you use WebWorkers, I can highly advise to use this, because it makes it so that you don't have to send messages back and forth, but instead you can sort of use an object-oriented approach. And here's a quick sort of example where in the main.ts file, you have your client code, like your React code that can call the WebWorker. And then in the WebWorker, you expose your class that you want to be available. And then all the methods on that class will be available via a sort of proxy object. Works really well. Yeah, quite happy about that approach. Now, here's a demo of 4 of our tools. To the left, you see the GrabCut, and this is just the videos of how it's being used interactively. And then we also have some other tools that allow you to very quickly find similar bounding boxes, or it allows you to annotate an object by drawing markers with watershed. Or we also implemented the polygon snapping tool with intelligent scissors. If you've used Adobe Photoshop, you'll probably have seen that, where you can draw around an object and it will automatically segment that for you. However, these classic models work really well if your data is clean. If your data is not clean, the results can be not so great. So it depends, like how good your input is and how good your data is. And the project that we're working on with Geti, we want that to be available for subject matter experts. And that means someone that might not be that technical, that might not know about data cleaning, and that doesn't have time for that. So we need something better. And that's why we came up with these smart tools with neural networks. And we implement 2, sort of 3, which I will cover now. The first thing we tried was an algorithm that's called reviving iterative training with mask guidance. And internally, we always call it RTM. It's essentially, you give it a point in a bounding box, and then it runs a neural net. It has a similar algorithm as segment anything, which I'll cover soon. This gives significantly better results for accuracy. And generally, the performance is also really good. Then in July 2023, I think roughly before that time, Meta announced a segment anything model. And the videos here show the results here. A really good foundational model that knows how objects work, like that knows the boundaries of objects, and that we now use for segmenting these models. Then after segment anything, and that's what I won't cover, but do want to shout out, is that we're working on this tooling called visual prompting, where essentially you use segment anything for your first image, and you remember the prompts you gave it, so you remember the points you clicked, and I'll go into that later, but and then use that to determine what points the user would click on a second image or a third image, and then you can do zero-shot learning. Now, I will now cover segment anything model more, go over the net architecture, go over what kind of pre-processing steps you need to do, post-processing steps, and then hopefully show a quick demo. Let me check the... I'm going to try to refresh. Yeah. This might break some other things later on, but that's okay. So the segment anything model, it's a foundational model from Meta. It was trained on 11 million images with 1 billion masks. So it knows a lot of images. It has this encoder and decoder architecture where you first send your image to an encoder, and that gives you image embeddings. And the workflow for this is that you first do some pre-processing on the image to make it so that it fits in the model, and then you get the embeddings out. Those embeddings are then sent to the decoder. Because one problem is that the encoder takes about 400 to 1,000 milliseconds to run. Can be slower on older devices or on bigger encoder architectures. So you don't want to run that a lot of times, because then you don't get that low latency. But this decoder is very fast. The decoder can run in about 50 to 100 milliseconds whenever you run it. And that means effectively for us that you can run it whenever you're hovering with your mouse over an image, and then you can keep getting the same results back. Yeah, so this gives us the accuracy and the refinability, because the accuracy comes from that foundational model. Refinability comes from the encoder-decoder architecture. You run the encoder once, then you run the decoder a lot of times, and you just rerun it until you get the good results. And the low latency comes from the good decoder. Now, before we go to, this could be a perfect fit. Before we go to the next steps, we need to figure out how do we run neural networks in the browser, because that's not really known to be a best place to run it. Most people just use Python, but you don't have that in the browser. There are some choices. There's this really good library that we did not use, which is called Transformer.js from Hugging Face, and they allow you to run a lot of models on the browser. They essentially just use ONNXRuntime underneath, but they do more pre- and post-processing steps for you. This was not out back when we started, so we did not use that. Then we are at Intel, and Intel has their own inference runtime, which is called OpenCV, but that does not work on the browser, so we could not use that. And then we basically got two choices. You have LightRT, which is a smaller version of TensorFlow, and honestly, we didn't really consider it. I don't remember why anymore, but it might be a good choice if you're starting out soon. Again, I think ONNXRuntime, that was our choice, and it works really well. It has some really good documentation, or decent documentation. And from what we see is this is being backed by Microsoft, and yeah, they want their models to run on ONNXRuntime. It's a sort of, really good runtime for general models. So how do we install it? Use your favorite package manager to install with npm install. And then I'll give a really minimal example of using it. Again, this is quite a bit of code. I will just show it in the slides just to emphasize, hey, you can run this locally if you want. You can try it out later on, and then we'll see. So first, you start out by fetching your model, and that can be done by via fetch or something else. It can also run in Node, so if you don't want to run it in the browser. Then you pass in the inputs that you create an inference session, and you need to know what kind of inputs and outputs you expect. And I don't have a really big background in deep learning or using neural network models, but one thing I found was very useful is Neutron.app, which you can use not just for ONNX, but also for a lot of other inference applications. And that will show you the graph of the model and then the inputs and the outputs that you have. Then, yeah, you run it. In this case, I just run a matrix vector multiplication, and that gives you a nice output. Some more notes. The Microsoft documentation is quite, they have a lot of different examples of how to run it. There's also examples of running a lot more fancy models, like DynoVV. You can run that in the browser as well. Next step would be that we need to choose an encoder. If you remember, the SAM has an encoder and a decoder architecture, and the quality of your data depends on the encoder, but also how long it takes. And when we started out with this, we had sort of three choices. We could use the original models that came from Meta, but they were quite big and slow to run in a browser. Like, it would take maybe 2 seconds to 30 seconds, and it was not that accurate. It was accurate, but yeah, it didn't work that great. Another was FastSam that we tried, and we found that that wasn't really accurate for our needs. I think it works better for a segment everything kind of model, where you're not interested in a single object, but everything in your image. So we went with MobileSam that had a really good balance between speed and accuracy. And what we see is it takes roughly 500 to 1,000 milliseconds to run. And that's fine, because that also, during the time we load models, we load our images, we do some other API requests. So oftentimes the user is waiting for other things while we do these computations. In 2025, there might be better choices as well. We didn't spend a lot of time in looking this up, but there's some really good literature about other models that you can use that I think could be faster and more accurate. But here we were pragmatic and we just stick with what we know. So just a quick recap. We have this encoder and a decoder. And for the encoder, you send your image, and then first you need to do some pre-processing steps. That's one thing I found with generally when trying to implement these bare neural networks, is that there's not a lot of great documentation about how to do these pre-processing steps and post-processing steps and what to look out for. Could also be because I'm not that well versed in the literature. So that's why I will spend a bit more time on how these steps, what kind of steps you need to do. First off, when you load the image, you remove the alpha channels, so the opacity, because that's not something we don't really care about. Then we need to do color normalization, and that just improves the accuracy generally. A lot of the models have been trained on MobileNet, and they have the input to those models are normalized based on the mean of the color space of those images. And if you do that for your input as well, that gives a lot better results. Same with resizing. Typically, models, when you run it with ONNXRuntime with inferencing and such, they have one specific size inputs that they give. In this case, 1024 by 1024, so you have to resize your image. And then fill in the rest with blanks. And these diagrams show you every step. And this I found quite funny when trying this out in the browser with these showing the intermediate steps. You have your original image that is 500 by 281. Then you normalize the colors, and it looks very trippy. It kind of looks like acid. So maybe this explains why a lot of LLMs are hallucinating. I don't know. Then you resize it. This looks the same, but essentially that's because it's the same diff. And we add some black padding. And that's it for the pre-processing steps. This image that you get, which is just a matrix or a tensor, however you want to call it, you send that to the neural net via the input, and then you get your embeddings out. When you get your embeddings out, you want to send that to the decoder every time the user interacts with the with your application. Yeah, okay. I need to double check something. Okay. When we do the post-processing for the decoder, so first, when you call the decoder, you have to provide the prompts. And basically what we provide is a point that the user clicks on, or if the user is hovering, we provide the location that the user is hovering on. So we give that point, and the model outputs 4 masks. The decoder outputs 4 masks. You can use different decoders as well, and I think in hindsight we should have used a different one, because basically what we always do is we pick the mask with the highest IOU score, and the output of the decoder always gives the IOU score and the mask itself. I still don't fully understand why it does that. It's probably in the paper itself, but I didn't spend that much time in really fully understanding that. So this is what we did. And then the next steps will be the same as GrabCut, where we take these masks. This one is not that obvious, but we take the mask, then we take the contour of that mask, so that we know the lines around it, and then we take the polygon of the mask, and that's the resulting output. So here you see, let me check if I can highlight this. No. Every point here will be the, yeah, that's the output polygon. Now, again, a recap to show you what all the steps that we did. We called the encoder, we got the image embeddings. Then after that, we used those embeddings, and we call the decoder every time the user hovers. And I need to check something. And we do the post-processing on that. Now, there's some optimization that we also did. Like I already mentioned, we use a lightweight encoder with mobile SAM. Another thing we do is that in our application, basically the user has to annotate a lot of different images. And when the user is annotating their current image, we just pre-compute the embeddings for the next image. We could also do this on the server and just do it on upload, but back when we started implementing this, we didn't have enough time to do this on the backend as well. Another optimization we do on the decoder side, that's in hindsight super obvious, but initially what we did is we would resize the masks that the model outputs back to the original size of the image. But some of our users use like high quality, really high resolution images like 3000 by 3000. And if you resize your mask to 3000 by 3000, that gets slow. Like it will grow by order n squared or something. So what we do instead is we compute the contour and the points that you would get based on the original size. And then we compute the points, and then we resize those individual points, which will be a lot less, and you don't need to do less interpolation. So that's, yeah, worked out really well. After we did this optimization, instead of our decoder step sometimes taking 400 milliseconds for really high resolution, it basically always is the same, about 100 milliseconds per hover that we do. Another really important step when you use neural networks in the browser is to have access to shared array buffer. This allows the WebWorkers to share the same raw memory across the same workers. And ONNXRuntime will fire up a lot of different WebWorkers to kind of do multi-threading. For this, you need your application to be served with these special headers, cross-origin opener policy and cross-origin embedder policy. The reason for this is Meltdown and Spectre, because without these headers, other tabs might be able to read into your raw memory, and then you get security issues, and we don't want that. Now, this is where I would have put a very interactive demo, but I didn't get that to work in time, so instead I'll show this image, this video, which is the original image video I showed at the start as well. So here you see me, whenever you hover over the egg, it shows the sort of output with a sort of opaque outline. And then when you click, you see the points that it gets, and it gives a really good experience. It kind of feels like this is we don't have to do much else to improve this. The only other thing would be the visual prompting that I mentioned. And just also to mention, if you do want to see the full demo, I will probably implement that full demo during the weekend, and then I will post it on GitHub. So if you want to see it, check it then. Now looking ahead, there's some very cool technology that is starting to get mature, namely WebGPU and web neural networks. With WebGPU, you have direct access to the GPU of the browser. The browser gives you direct access to the GPU. And yeah, with that, you can do all your fancy things that you would do natively. In my experience, especially on Linux, it doesn't work that well yet. Like if you want to run it in Chrome, you have to enable some flags. But it's starting to get more mature, and I think in Windows it's enabled by default. You also have web neural networks, which essentially is a library that the browser exposes, which often frameworks like ONNXRuntime, LightRT, etc., they will use. And then you get direct access to the native inference runtimes. For instance, ONNXRuntime compiled to C++ or OpenVINO if you're on the Intel hardware, and that makes it a lot faster. And actually, the results that you saw before, they were all, like in the demo of the mask decoder, those were running in the browser in these slides with WebNN, but I did have to enable those flags. ONNXRuntime has full support for this, but yeah, I did find that sometimes it doesn't work, and typically I do prefer the CPU because it feels a bit more stable. And we need to do a bit more experimentation to figure out if it's valuable for us to switch over to WebGPU or WebNN. These are links that direct to the documentation pages of ONNXRuntime. Transformers.js also has this same support because they use ONNXRuntime, and they have some really good cool demos where you can use Dino v3 to do video tracking, where you upload a video, you select a point in the video, and it will track that same object throughout the video. And does that fully in the browser. You don't need to install any packages at all, only download the source code of that website, which might still be a lot of data, but you don't have to do the whole dependency management. And I think that's very cool. So as I mentioned, this presentation itself uses WebNN internally. But the demo that I wanted to show before didn't fully work out. And that's partially also because this is still experimental. And I had some issues with my slide software. Now there's only a few slides left. Some other applications that you can use these kind of tools for, because we are kind of building a niche thing that we are building this annotation software. But you can use it for like active learning to figure out which images you need to annotate. For when you're in the medical field, you can use this to annotate healthcare problems, cancer, etc. and things. You can use it for automatic background removal if you're making video software, visual search. And another cool thing might be useful is if you combine it with an LLM and OCR, where you use the segment anything to understand what objects are there, and then you provide that to an LLM to describe what it is, and then you have some better accessibility. That's all that I will share about these visual tools. I want to do one more shout out to my other colleagues that are sitting there. They will give a presentation about Anomalib, about near zero defects, and that's in camera 2 after the break. And with that, I want to thank you all for listening.
All right, give an applause.